Welcome to the deep dive. We sift through a mountain of research so you don't have to.
Yeah.
And today we're diving into, well, this is going to sound a little wild, quantum teleportation in chemistry.
Yeah, that's not something you hear every day, is it?
Not exactly your typical water cooler talk, but here's the thing. It's real. It's happening. And we're going to break down what it is, why it matters, and how it could change, well, practically everything about the field of chemistry. And I've got our expert guide here with us today to help us make sense of it all.
I'm happy to try to shed some light on it, because really, this is pushing the boundaries of what we thought was possible.
Okay, so first things first. When I hear quantum teleportation, my mind goes straight to Star Trek. Right? Beam me up, Scotty. But I'm guessing we're not talking about transporting people or even beakers full of chemicals across space, are we?
Not quite yet, anyway, though who knows what the future holds. But no, when we're talking about quantum teleportation in chemistry, what we're really focused on is information.
Information.
Yeah, like instantly transferring information about a particle's state. Imagine knowing everything about a molecule down to the tiniest detail, no matter how far away it is. That's the potential power we're talking about here.
Oh, wait, my brain is already starting to hurt a little. How can information travel instantly? That feels like breaking some fundamental law of physics to me.
It does seem counterintuitive, doesn't it? But the key to all of this is a concept called entanglement.
Entanglement.
Yeah, it's where you have two particles linked so tightly, so intimately, that they basically act as one. No matter how far apart they are, if you change one, the other changes instantly.
Whoa.
Yeah, Einstein famously called it spooky action at a distance.
Spooky is a pretty good word for it. So this entanglement, it's what makes quantum teleportation even possible.
Yeah, exactly.
Okay, all right, hang on. We've got instant information transfer and we've got spooky entanglement. But you said that scientists are already exploring this with molecules. What does that even look like? I mean, how do you entangle a molecule?
Well, think of it this way. Researchers are starting to see how entanglement could lead to types of chemical bonds that we've never seen before.
New kinds of bonds.
Yeah. Imagine bonds where the atoms aren't physically connected in the traditional sense, but they're still influencing each other. That's a whole new level of molecular interaction, and it could completely rewrite our understanding of how molecules behave.
So this is more than just theoretical. Scientists are actually seeing evidence of this happening.
It's still early days, but the potential is enormous. I mean, think about it. Instantaneous information transfer, potentially game-changing chemical bonds. Where does this lead us? What can we actually do with all of this?
That's the question, isn't it? It's all very mind-bending, but how do we actually apply this quantum weirdness in the real world?
Well, that's where things get really exciting, because we have to talk about quantum computers.
Quantum computers. Everyone's talking about them, but they always seem so mysterious.
Well, the key is that these quantum computers are being designed specifically to leverage these very principles we've been talking about: entanglement, superposition, all of that. And the potential is huge. We could be talking about computers that are millions of times faster than anything we have today.
Okay, so faster computers, that's going to be good for something, right?
Yeah.
But how does this translate to, say, something like drug discovery? What does it actually look like?
Think of it this way. It's not just about speed. It's about tackling problems that are so complex that our current computers just can't handle them.
Like what? Give me an example.
Okay, imagine trying to simulate how a new drug interacts with a specific protein in the body, down to the atomic level.
Okay, I can see where the complexity comes in there.
Yeah.
But, I mean, we already test how drugs work, right? We've got clinical trials and labs and all that.
We do, but those methods, they're slow, and they're often imprecise. It's like we're trying to understand these incredibly intricate molecular interactions using tools that are like blurry photographs, you know? We can kind of see what's happening, but the details are fuzzy.
Okay, I'm with you. So where do quantum computers fit in?
With quantum computers, we could have high-definition 3D models of these interactions. We could see exactly how a drug molecule fits into a protein, how it binds, how it changes shape. We could actually see the mechanism of action in all its glory.
So instead of just throwing things at the wall and seeing what sticks, we could actually design drugs with a very specific purpose, knowing exactly how they'll work.
Exactly. And not only that, we could test thousands, maybe even millions of potential drug candidates simultaneously.
Whoa, hold on. Millions.
That's the power of quantum computing. It's not just one calculation at a time. It's exploring a vast number of possibilities all at once.
That's mind-blowing. So we're talking about faster drug discovery, more effective drugs, fewer side effects.
And potentially truly personalized medicine. Imagine designing a drug that's perfectly tailored to an individual's genetic makeup and the specific proteins involved in their illness.
Personalized medicine.
Exactly.
That sounds straight out of science fiction. But this isn't just about drugs, is it? You mentioned material science earlier.
Oh, the applications are vast. Imagine designing materials with properties we've only dreamed of, lighter than air, yet stronger than steel. Or materials that can conduct electricity with zero resistance at room temperature.
Okay, now you're just showing off.
Uh,
Super strong, lightweight materials for building, lossless energy transfer. That would revolutionize entire industries. This all sounds incredible, but it makes me wonder, what's holding us back? Why aren't we living in this quantum-powered future already?
Well, there are some hurdles to overcome, and one of the biggest is scaling up these quantum computers. The ones we have now are incredibly sensitive, they're finicky, they need very specific conditions to operate. It's a huge engineering challenge to build ones that are powerful enough and stable enough to tackle really complex chemical problems.
So it's not as simple as flipping a switch and turning on the quantum revolution.
Not quite, but researchers are making incredible progress all the time. And it's not just about the hardware, it's also about the software.
The software.
Yeah. We need to develop sophisticated quantum algorithms, basically, the instructions that tell the quantum computer what to do. And these algorithms need to be incredibly efficient and incredibly accurate to make the most of the quantum computer's power.
So better hardware, better software. It's a two-pronged approach. But I have to ask, what's the timeline here? When can we realistically expect to see this quantum magic impacting our everyday lives?
It's tough to say for sure, but there's definitely a sense of excitement and urgency in the field. Some experts believe we could see some major breakthroughs within the next decade or two, maybe even sooner.
So not teleportation devices for my next vacation, but maybe life-saving drugs and game-changing materials within our lifetime. I can get behind that.
It's definitely a future worth getting excited about.
Absolutely. But before we get too carried away, there's one more piece of this quantum puzzle that we haven't talked about yet. And this one, I have to admit, really boggles my mind. Superposition.
Ah, yes, superposition. It's definitely one of the weirder aspects of quantum mechanics.
Weirder than teleportation. You're really raising the bar here.
Well, just think about it for a second. It's the idea that a particle can exist in multiple states at the same time. Until we measure it, until we observe it, it's not that we just don't know its state, it's that it's actually in all those states simultaneously.
So it's like, it's not just spinning a coin and not knowing if it's heads or tails. It's like the coin is both heads and tails at the same time.
You got it. It defies our everyday logic, but that's the quantum world for you.
All right, I think I'm sort of following. But how does this superposition thing even apply to chemistry? I mean, molecules are made of atoms. Atoms are particles. Does that mean molecules can be in multiple states at once, too?
That's exactly what it means. Imagine a molecule that's not fixed in one specific shape, but it's constantly fluctuating, shifting between different configurations, all at the same time.
Well, wait a minute. So we're not just talking about speeding up existing chemical reactions here. We're talking about potentially unlocking entirely new possibilities, reactions that just couldn't happen before.
That's the potential, yes. It's like opening up a whole new dimension of chemistry with reactions and processes that we can't even imagine right now.
Okay, my brain is officially fried. This is incredible. We've gone from teleporting information to creating new kinds of chemical bonds to molecules existing in multiple states at once. We're not just talking about tweaking the edges of chemistry here. This sounds like a complete revolution.
It's definitely a paradigm shift, and it raises some really big questions about what the future of chemistry holds.
Big questions indeed. So where do we go from here? What are the next steps?
Yeah, it's definitely a paradigm shift. And like you said, it really does make you wonder what the future of chemistry looks like with all of this in play.
Exactly. It's exciting, but it's also a little intimidating. It feels like we're on the verge of a whole new era where the rules we thought we knew are being completely rewritten.
I think that's a pretty good way to put it. It really does challenge our conventional understanding of how molecules behave.
Yeah.
But honestly, that's what makes science so fascinating, isn't it? Pushing the boundaries of what we thought was possible.
Absolutely. So where do we go from here? What are the next big steps in this field?
Well, it's a multifaceted challenge, that's for sure. We need to keep pushing the boundaries of quantum computing hardware, to handle even more complex calculations. We need to develop better and better algorithms to make the most of that computing power.
Okay, so the hardware and the software, the classic tech combo. But is there anything else?
The biggest thing, maybe even more important than the hardware and software, is collaboration. We need chemists, physicists, computer scientists all working together, bringing their expertise to the table. bridging the gap between theory and application.
Makes sense. It sounds like a truly interdisciplinary effort. So, what are the biggest unanswered questions right now? What are the mysteries that researchers are most eager to solve?
Hmm, that's a tough one. There's so much we still don't know. But one of the most intriguing questions, I think, is how to really control and manipulate entanglement on a larger scale.
Okay, back to entanglement. So we've seen it in the lab, but what about in the real world?
Exactly. We've seen the potential, but how do we actually use it to create, say, macroscopic materials with entirely new properties? That's the challenge.
So materials that have properties we haven't even thought of yet.
Precisely. I
Yeah.
mean, imagine materials that are self-healing or materials that can change their properties on demand depending on the conditions. The possibilities are almost limitless.
It's like taking these mind-bending quantum principles and scaling them up to the everyday world. That's incredible. But it also makes me think about the ethical considerations. As we start to gain more and more control over matter at this fundamental level, are there any potential downsides we need to be thinking about?
Absolutely. That's a really crucial point. It's not just about the science itself. It's about how we use that science responsibly. As with any powerful technology, there's potential for both good and bad.
Yeah.
We need to be having open and honest discussions about the ethical implications of these advances, making sure that these technologies are used to benefit humanity.
I completely agree. It's not just about the breakthroughs. It's about making sure those breakthroughs are used for good. Well, I don't know about you, but my head is spinning after all of that. This has been an incredible journey into the world of quantum teleportation chemistry.
Yeah, it's definitely a field that's full of surprises, and who knows what the future holds.
That's the beauty of it, right? The possibilities are endless.
Yeah.
And it's just so exciting to think about what might be possible.
Absolutely. I think it's safe to say that we're only just scratching the surface of what quantum mechanics can do for chemistry.
Well, on that note, I think it's time for us to wrap up this deep dive. But before we go, I want to thank you for joining us, and a huge thank you to our expert guide for taking us on this incredible journey into the quantum realm.
It was my pleasure. I'm always happy to talk about the wonders of quantum chemistry.
And to our listeners, we hope this has sparked your curiosity about the incredible world of quantum chemistry. It's a field that's evolving rapidly, and we can't wait to see what the future holds. So stay curious, explore further, and join us next time for another deep dive into the world of cutting-edge science.